Hello, dual enrollment folks. This is Miss Backfish, and this is in dual enrollment pre-calculus, and we are entering the pre-calc, the trig really part of this semester with talking about angles in both degrees and radians, and that's what we're doing in section 4.1. So let's start out first, having trouble with words today, sorry, with the very simplest way to look at some angles, and that is their size, classifying them. And I know that you know this. You just quick remembering, again with the words. Acute angles are angles that measure between 0 and 90 degrees. Let's say X is my angle measure. All right. Obtuse angles. Sometimes we think of those as angles that are greater than 90, but really it's generally between 90 and 180. Okay, and when we talk about obtuse angles. Right angles, of course, are 90-degree angles. And finally, straight angles. A straight angle is basically just 180. It's a line. So at the beginning of your homework, you're just being asked to classify angles based on these simple classifications that you used at the very beginning of geometry. And I know you will not have any trouble doing that. Next, we start to look at degrees versus radians. And notice I did all of these in degrees. Okay, so what are radians? What is a radian? It's basically a way to look at angle measure with respect to a circle. It's not a perfect circle, but that's not too bad. And basically it's talking about thinking about a circle is 360 degrees. Like, so for instance, this angle here that I'm going to mark like this, that angle might be 135 degrees or something like that. All right. But we're not going to look at it in degrees. Okay. Degrees meaning out of 360. So 135 degrees, maybe a little bit more than a third of 360. We're going to look at it with respect to length, and that includes with the radius. So radians are basically like asking how many radiuses, how many times could I lay the radius down going that far? So it's like, here's the length of my radius, and I say, okay, if I were to pick that up and lay it here, and then it would go this far around, and then lay it here. That's another length of the radius. So each of these is the length of the radius, and then a little bit more, a little portion of the radius. So let's say this could be maybe like 2.3 radians or something like that. That's what radians is. And since it's based on the radius, and it's really talking about this angle more in terms of almost like a length around the outside. Remember, the length around the whole circle is the circumference. So that means how many radians is all the way around? Well, just like this says how many times the radius do you have to go all the way around? 2 pi times the radius gets me all the way around. So 2 pi is about 6. It's a little bit bigger than 6, right? About 6.28. There's about 6.28 radiuses going all the way around. So go here. This is if I picked up the radius and laid it down. And I'm running out of space. Here we go. It would take me around 1, 2, 3, 4, 5, 6.28 times to get all the way around the circle. So that's what we're really doing here, is we're really explaining how to get around the outside of the circle, or how to get that many, walk around through that many degrees in terms of length with respect to the radius. So in degrees, an entire circle is 360 degrees. In radians, an entire circle is 2 pi. It's 2 pi radiuses. That's really exactly what radians is. It's how many radiuses could you fit in this portion of the circle. Okay, so if a whole circle is 360 degrees, then what would a half circle be? It's 180 degrees. Answer my own question there. But if a whole circle is 2 pi radians, then a half circle, 180 degrees, would be 1 pi, half of that. Half of 2 of something is 1 of that thing. This is what we use then as our conversion factor. Okay? That 180 degrees is equal to 1 pi radians. I don't know why I wrote it that way. 180 degrees is equal to pi radians is a much better way to write it. Okay, so we're going to use that to convert. If I want to go from degrees to radians, okay, then that means that's like saying I want to divide out the degrees. So I'm going to put the 180 in the denominator. And I'm going to put the pi up top. Okay, so one way of thinking about that is if I'm starting in degrees and I want to end up in radians, I need to cancel out degrees so the degrees go in the denominator. Another way to think of it, I usually think of it, is numerator is whatever I want to end up with. If I want to end up in radians, then I need to put the pi on top because the pi refers to radians. If I wanted to go the other direction, then the degrees need to be on top because I want to end up in degrees. So that's what we'll do to get from degrees to radians. We always use 180 degrees equals pi radians, and we multiply by either pi over 180 or 180 over pi. And again, I think the easiest way to decide which is if I want radians as my final answer, then the thing that refers to radians goes on top. If I want degrees as my final answer, then the thing that refers to degrees goes on top. So let's look at a couple of examples like that. Okay, so here we're being asked to convert these angle measures in radians to degrees. And sometimes it would say RAD to let us know it was in radians. But if it's got a pi symbol in it, that's a pretty good hint too. So I'm going to take my radians, and if I want them to end up in degrees, I'm going to multiply by 180 on top. And then these will cancel. 180 divided by 3 gives me 60 degrees. Okay, so a lot of times it's easier to do it by hand than to stick it in your calculator because things are going to cancel out. Same goes here. If I want to turn this into a degree measure, multiply by 180 over pi. My pi's cancel out. 180 is divisible by 6, so I'm going to cross cancel here. 6 goes into itself once, and it goes into 180 30 times. So really I just have 11 times 30, which is 330 degrees. Now let me point out, radians don't always have to be in terms of pi. You could have radians in decimals. You could have, for instance, let's say you have 1.9 radians. Okay, if it's already in decimals, then go ahead and give your answer in decimals, but we'll still multiply by 180 over pi, and then I would use my calculator. Okay, and so I'd get 1.9 times 180, and then I would divide by pi, and I'd say, oh, it's 108.86 degrees. Let's go ahead and do it to the hundredths. All right, now we can also go the other way. We can go from degrees to radians, and usually when we do that, since look at how often radians are basically written in exact form, in other words, with a pi symbol and with fractions, we generally do try to keep it in exact form. Okay, so when we're going from degrees to radians, I'm going to multiply by pi over 180. All right, so basically when you're multiplying fractions, this is like over 1, top times top, bottom times bottom, and basically I'm just reducing. Keep an eye out for that if you're being asked for exact form, don't give a decimal, don't put it in your calculator, except to reduce. Calculators like this can help me reduce. 134 divided by 180. As a fraction, that is 67/90ths. So my final answer would be 67 pi over 90. All right, let's do another one. Let's say I've got 90 degrees. Why not? Okay, remember that 180 is equal to pi. That's why we're multiplying by pi over 180. If 180 is pi, then 90 should be half of pi. 90 over 180 simplifies to 1 over 2. So this is how we write half of pi. So 90 degrees is pi over 2. All right. What if you're asked to give your answer in decimal form? Well, then you use your calculator. Like let's say we have, 234 degrees, and we're asked to put that in radian form. Then I would do 234 times pi on top, and then I would divide by 180, and I get 4.08, or about 4.08. So radians can be decimals as well. Okay, so I wanted to come back to this picture for just a second because I wanted to point out to you that this angle, I drew this way, not just randomly. I drew it that way because that is a very standard way that we draw angles when we're talking about angles of rotation, angles with respect to circles. And that's called standard position. That's why it's a standard way to do it. And what I mean by that is, if an angle's in standard position, that means it has one side that points, you could think of it as due east, okay, or along the positive x-axis, going to the right, positive x-axis, okay, and that's sort of my beginning point. That's like 0 degrees, or 0 radians, 0 pi, okay, and we rotate counterclockwise from there. So that would mean my other arm of my angle might be like here, something like that. So standard position has one side of the angle, one of the rays, pointing right here to the right. Here's the center of your circle. There's the beginning. So we know that this is the angle I have rotated through to get to what we call our terminal side of the angle. This is the initial side of the angle. This is the terminal side of the angle. Initial means beginning. Terminal side means ending. So that's why we call it that. So here's the initial side, terminal side. And it's basically implying that I have rotated through that turn. Okay? Now, you're going to be asked some questions about what, if you put this in standard form or a standard position, in what quadrant would your terminal side be? So we got to remember our quadrants. Let's go ahead and draw right through here. Okay, quadrant 1, quadrant 2, quadrant 3, quadrant 4. Those are standard. Those are always in the same places that they have been ever since you first talked about them in Algebra 1. Okay, so let's suppose that you are asked to draw the angle pi over 3, which tells me they're using radians to measure it, and you're asked to draw it in standard position. Okay, well, we already know that this is where we're going to start. So our initial side has to go point over here. This is like my 0. So this is, in this case, we're not using degrees, we're using radians. So this is like 0 pi. All right. Now, we talked earlier about how 180 degrees was the same as 1 pi. So that means if I go halfway around the circle, this is 1 pi. So what is pi over 3? That's the same as a third of pi. So if I'm going a third of pi, then I'm going a third of this semicircle. And that's the worst semicircle I think I've ever drawn. Okay, I'm going a third of that semicircle. Okay, so this is the whole. 1/3 of that would be maybe somewhere like this. And that's where my terminal side would go. So this is 1/3 of pi, or pi over 3. And that's how we measure angles rotationally when we're talking about rotational angles in radians. So I'm going to show you a few more of those. And let's just go ahead and work our way around the whole circle. And I am drawing, I've got some templates that are much better circles than this. So you'll be happy to know that. Okay, now if you're watching this video, I know that many of you have already had PreCalc or trig, and you feel like you understand this, or you feel like you don't understand it and you don't care because you didn't like radians and you just always changed them to degrees. If you will take the time to really try to understand what I'm showing you right here, it makes life so much easier. And that is, again, remember we're going to start, this is our 0. This is pi. Okay? So going from here across the top of the circle, that's 1 pi. So let's think about what that would be in thirds. If I cut that into 3 pieces, this is where my cuts would be made. If I made my cuts right here, that would be in 3 pieces. So this is 1/3 of pi, which is the same thing as pi over 3. And this is 2/3 of pi, or 2 pi over 3. Here's pi. If I follow those lines through the origin, and I'm cutting the bottom part of the circle into 3 pieces as well, 1, 2, 3, we still have thirds. So 1/3, 2/3, 3/3 is the same as 1. So that's why that's 1 pi. 4/3, 5/3, and 6/3 is the same as 2. So we can also think of all the way around as 2 pi. Remember, that goes with our circumference formula. 2 pi times the radius is all the way around. So 2 pi is all the way around our circle. So this is breaking it into thirds. Okay? Now I could do the same thing with fourths instead. I'm not going to do that. All right, fourths. This is 1 pi. All of this is pi going across the top. To break that into 4 pieces, well, I could think of this as already 2 pieces. So going right through the middle of each quadrant breaks it into 4 pieces. 4 pieces is the same as fourths. So this is 1/4 of pi. This is 2/4 of pi. This is 3/4 of pi. And this is 4/4 of pi. That's the same thing as 1 pi. I can keep going with the line that goes right down the middle through each quadrant and have 5/4, 6/4, and 7/4. And then back around here, I've got 8/4, which is the same as 2 pi. Now let's reduce these other ones. 2 pi over 4, 2/4 is the same as 1/2. So pi over 2 is 90 degrees. We already said 4/4 is the same as 1. 6/4 is the same as 3 over 2. So that's where that is. So these are the lines right in the middle of each quadrant. And we're back here, I was dividing into thirds. So it's this line here. And now we're going to go ahead and take this same picture and go ahead and think of it in sixths. Instead of having 3 pieces of pi, I'm going to take this half circle, this top half circle, 1 pi, and divide it into 6 pieces. That means each one of these 3 pieces, I draw a line right down the middle of. So this is 1/6 of pi, 2/6 of pi. 2/6 reduces to 1/3, so it's still 1/3. 3/6 of pi. Remember, 3/6 reduces to 1/2, so it's still 1/2. 4/6, which reduces to 2 pi over 3. 5/6 doesn't reduce. 6/6 would be 1. Here's 7/6, 8/6, which reduces to 4/3. 9/6, which reduces to 3/2. 10/6, which reduces to 5/3. And 11/6. All the way around is 12/6, which is still 2. Okay, so if I'm asked to graph, for instance, okay, so for some reason my video glitched here and jumped, and this was me showing you what to do if you have a negative angle. When we have positive angles, like this would be 5 pi over 3, which is 5/3. I do 1/3, 2/3, 3/3, 4/3, 5/3. and I'm always rotating counterclockwise. Here I've got 3/4 of pi. 3 pi over 4 means 3/4 of pi. So I divided it up into fourths. Those are the lines right in the middle of each quadrant. I said 1/4, 2/4, here's 3/4. If I were to go negative, if I were to try to graph a negative angle, or I'm using a negative angle, that just means instead of rotating counterclockwise, go backwards, go clockwise. So this is negative 2/3 pi. Negative 1/3, negative 2/3. Okay? Now, the last thing we need to talk about here is arc length. And arc length is something you dealt with in geometry. It's a part. It's not arc measure. It's not degrees. Arc length is saying a piece of the circumference, a piece of the distance around the circle. So, for instance, there's a circle and you're being asked, what is the length of this arc? Like, what is the distance an ant would walk if I put him on a track and made him walk that far? Arc measure is degrees. Arc length is like centimeters or inches or feet or whatever. It's a unit of length. Now, when we were talking about this in geometry, we said, if you could figure out what the central angle is associated with your arc, if you know that, and we're going to call it theta, then our arc length is proportional to the part of the whole circle that that angle is. For instance, if that angle is 90 degrees, that's a quarter of the circle. So my arc length would be a quarter of the circumference. If that angle is 120 degrees, well, that's a third of the circle. So my arc length would be a third of the circumference. So it's always a piece of the circumference. So the way that worked in geometry was however many degrees out of 360 you're talking about, times the circumference. And here's the circumference formula. Okay? But if you look at this formula, the only part of it that really is degree specific is right here. So if this was not in degrees anymore, if this was in radians, well, instead of 360 underneath it, what's all the way around a circle in radians? Instead of 360, it's 2 pi. So then my formula becomes theta times 2 pi r, because this is like over 1. So times 2 times pi times r, all over 2 times pi times 1. What happens? That goes away. So arc length when your angle is already in radians is beautifully simple. We use an S to stand for it, and I really have no idea why. If anybody knows, please tell me. We use an S to stand for arc length. And it's just whatever the angle is, the central angle in radians, times the radius. So this is the radius, and this is your central angle in radians. So it has to be in radians for this to be the formula. But if we know we're working with radians, it's just beautifully simple. It's just the radius times the radians. There are a couple of formulas, a couple of problems in your homework where you're asked to use that, and I think you'll find them very straightforward as long as you're using that equation. So that is pretty much section 4.1. I hope you enjoy it, and I hope you work really hard at trying to understand the fractions of pi in terms of our angle measures in radians, because it's going to make life a whole lot easier for you if you actually can see, oh, this is where pi over 3 is, or this is where 4 pi over 3 is, as we get into using these things with trigonometry. Thanks so much, and I will see you later.